Okay, 6.5, comparing functions, is our last section for Unit 6. We're going to apply what we've learned in the last section to compare each representation below. We want to know which two of these are the same function. So the first thing we're going to decide is if they're linear, quadratic, exponential, or absolute value, and explain how we know, or show some work to support how we know. The trick then is going to be if there's 3 that are quadratic, then we have to see, okay, if we plot some points, which 2 are actually the same. Okay, so looking at this first one here, making our tables to go from -7 to -5, -5 to -3, -3 to -1. That's up 2 each time. So because it's changing at a constant rate, we know that means it's linear. So that's a straight line. Okay. This one has an x squared. I know because it has an x squared that this is quadratic. I'm just going to say that's my reasoning. There's an x squared. This, because it's U-shaped, is also quadratic. And then this one here, because it has an x in the exponent, I know that's exponential. Okay, so the only two that are the same type are these two right here. So these two are the same. All right, looking at the next example. Here, these bars, because of the bars, I know it's absolute value. Okay, this is L-shaped. So it's exponential. This is straight, so this is a line. And then this one here, if we look from 4 to 16, from 16 to 34, well, that's times 4. You're multiplying between each one, that's exponential. And because it's going up, that's growth. Oh, actually that's backward because these are going down. Sorry, that would be decay. Because really this would look like 0, 4, but then -2, 16. So that would be way up high. It would go like this. That is going to be decay. All right, and then this has an x with no exponent. So I know that's linear. Okay. So looking at this, I only have one absolute value, one exponential. Well, these are both exponential. These are both linear. I need to know which one matches. So here, I said 0, 4. Well, 0, 4 would be way up here. This is not on this line. So these two do not match. This one doesn't have anything it could match with. So that leaves these two. And if I want to check, I need to solve this for y. I add the 5x over. And this does cross at +4. And then go up 5 over 1 or down 5 back 1. Up 5 over 1. Okay, so these two do match. Those are the same function. All right, we're going to look at one more of those. So moving on. We have one more example like that. The first one here is V-shaped. And you're getting really good at telling me that V-shaped means that it's absolute value. Okay, this one right here has a squared, so it has an x squared. It just looks a little different. So because it has an x squared, it's quadratic. This one I can look, we're going -1, -1. So because that's constant, adding or subtracting the same number each time, we know it's linear. Look at this one, however, we can't really see what's going on here, because from here to here, that's down 2, but then from here to here, that's up 6, and we don't have enough information. We need another term to find the second difference. So we don't really know what this is. So we'll see if we can find two that are the same before that. Okay, this one, because it has the bars, we know it's absolute value. Now comparing, we know the negative flips it over. This one's flipped over. The +3 takes it over 3, left 3, and the -2 takes it down 2. That seems very reasonable with this graph right here, so these two must be the same. Alright, and then we have another one here. We're looking at parallel and perpendicular lines. So this is only for linear. If we have two lines, we can compare them and see if they're parallel or if they're perpendicular. So parallel lines are two lines that go on forever and they never intersect. Try to draw parallel lines here. To be parallel lines, they have to rise and run at the same rate. The rates of change have to be the same, which means we have to have the same slope. So an example here would be like y equals 2x plus 1 and y equals 2x minus 5. So those have different y-intercepts. The slopes are the same, so they're rising and running at the same rate. The other option is to have perpendicular lines. Perpendicular lines meet at a 90-degree angle. That's what this little box usually stands for, 90 degrees. They meet at 90 degrees, and for that to happen, we have to have opposite reciprocal slopes. Meaning they have opposite signs and it's flipped over. It's a reciprocal. So for instance, if I had y equals -1/3 x plus something, anything, then I would take this and change the sign. So now instead of negative, it would be positive, and flip it over. So instead of 1/3, it would be 3/1, or just 3. And then maybe it has a y-intercept of -4. I feel like that one's a little more tricky, so maybe we want a second example. We could have like y equals 2/3 x, and maybe it doesn't. Maybe the y-intercept's 0, so it's just that. And then a line that would be perpendicular to that might be y equals negative, change the sign and flip it, 3/2 x plus something, it doesn't matter what. Okay. Those lines would be perpendicular. So if you need to decide, you need to make sure they're solved for y, look at the slopes. If the slopes are the same, they're parallel. The slopes are opposite reciprocals, so opposite signs and flipped. Then, like these two examples, then they're perpendicular. Okay, we've got one more example to look at. It says, Tell me graph the equation y equals 2x minus 3. Write a new equation that has double the slope and the y-intercept is increased by 3. Well, my slope here is 2, so if I'm going to double the slope, my slope would be 4. And then to increase the y-intercept by 3 instead of minus 3, if I add 3 to that, that's just 0. So I could write plus 0, or I could just leave it y equals 4x. Adding 0 doesn't change it. Okay, this new line, y equals 4x, these slopes are not the same, so they're not parallel. Not the same. The opposite reciprocal of 2 would be negative 1/2. You change the sign and flip it. This is not negative 1/2. So it's not perpendicular, so it's just intersecting. That's it. All right. Thanks for watching.